Now, let's look at two examples of two-dimensional dynamical systems. We have two differential equations over here. What it means is that now we have two quantities. They are changing in time. So, to find an equilibrium, we still solve the equation from the right-hand side, set the equation to zeros. So what we have over here is that to find equilibrium, now we have two components, x star and y star. How to find them? We solve a pair of equations simultaneously. So we have 50y minus 1 minus 0.05x is equal to 0. You may wonder why this example looks like this, because it is from an application, so we get this kind of pair of equations. Now to solve this system, we start from the second one, because point 1 times y is equal to 2, so 0.1 times y is equal to 2, and we have y star is equal to 20. Multiply 10 both sides. If y is 20, then we plug in the equations, so 50 over here and 20 minus 1, and then we will be able to solve x, and this is equal to 0. So we have 50 times 19 and is equal to 0.05x. Multiply 20 both sides, so we will have x is equal to 19,000. It's a big number. So that's our equilibrium. We have two components. Now let's look at stability. To do stability, we need to find the Jacobian of this dynamical system or the function on the right hand side. Usually we say it's vector field. So how do we do that? So we can say this is the one. We have f of x, y is equal to 50 y minus 1 minus 0.05 and x. And we have another function g of x, y is equal to 0.1 y minus 2. The Jacobian matrix is four partial derivatives. We have partial f, partial x, partial f, partial y, and partial g, partial x, partial g, partial y. Fortunately, we have just linear functions, so it's easy to find the derivatives. And if you take the derivative with respect to x for the first one, we have 0.05. And take the derivative with respect to y, we get 50. And for the second one, we have 0 over here, and then we have 0.1. Okay. Now, if you look at this matrix, we can find easily eigenvalue. Because here, you see, this is upper triangular matrix. We have 0 over here. So two eigenvalues are the following. Lambda 1 is simply negative 0.05, and lambda 2 is 0.1. First eigenvalue is less than 0, and second eigenvalue is positive. As long as you see one eigenvalue is positive, it is unstable. So what we have over here, x star, y star over here, is unstable. Now, how can we see the dynamics? What is the geometrical method? Here we need to be very careful, but we will do that one in another section. This is the derivative method determining the stability. First, we find the equilibrium by setting two equations to 0. And then we evaluate the Jacobian matrix. And then we find eigenvalues. In general, eigenvalues can be found by solving linear systems, but here we solved this one by simple observation. Let's look at our second example over here, number 2. And find equilibrium. We solve a pair of equations. We have negative x plus y is equal to 0, and negative x minus y is equal to 0. And we can easily see that solutions we have 0, 0. There's only one solution. X is equal to y from the first one, and then negative 2y is equal to 0. We have y is equal to 0, and so x is also equal to 0. So 0, 0 is the only equilibrium. Is the only equilibrium. Right? So now let's find the Jacobian matrix. Take the partial derivatives. We have f of xy, the first equation, is negative x plus y. And g of xy is negative x minus y. Right? So take the partial derivatives. We have negative 1, 1, and negative 1, negative 1. How can we find eigenvalues? We can solve the equation. We can say the equation is this: is negative is lambda I minus a its determinant is equal to 0. Or we can say find the determinant of lambda minus negative 1 becomes plus 1, and minus 1, and plus 1 over here, and lambda plus 1. So what's the determinant of this one? And that's going to be lambda plus 1 squared and plus 1. That's the determinant, and then we set this one to 0. And remember, this one we have complex solutions. We have lambda plus 1 squared is equal to negative 1, so lambda plus 1 is equal to plus minus imaginary unit I, and then we have lambda is equal to plus minus negative 1, just negative 1, it's negative 1 plus minus I, so lambda 1, 2 is equal to negative 1 plus minus I. And if you look at the real part of lambda is negative 1. When the real part of lambda is negative 1, this is stable. So 0, 0 is stable. We look at the real part of both eigenvalues. If it's negative, then we have stable equilibrium. In next video, we are going to explain how we can visualize this type of stability by using the method called the locus method or the null climb method.